Hey y'all, today is March 18th and this is your homework from last night on theoretical and experimental probability. So let's get started checking and correcting our homework. So number one, a number between 1 and 3 is chosen 30 times. Results are shown in the table below. So part A, find and compare the theoretical probability and experimental probability of choosing a 2. Now remember, theoretical probability is what should happen. Okay, so if a number between 1 and 3 is chosen, we want to know what is the theoretical probability of choosing a 2. Well, 2 is just one number out of 3 possible options. So remember, we write our probability as the number of favorable outcomes over the total number of outcomes. So 1/3. I can't reduce that fraction, but I can write it as a decimal or as a percent, just so it's easier to compare, because a lot of times our fractions won't have the same denominator. So I'm going to write this as a decimal, and to write this as a decimal in my calculator, I just put 1 divided by 3, and I get 0.3 repeating. So 0.3 repeating, right? Now, let's look at the experimental probability. Okay, so the experimental probability is what actually happens. So we know that the numbers between 1 and 3 were chosen 30 times, and we can see clearly that 2 was chosen 12 times. So 12 favorable outcomes, that's my numerator, over 30 total outcomes. Well, 12 divided by 30, I can reduce, so 2 goes into both of those. 2 goes into 12 6 times, and 2 goes into 30 15 times. I can actually still reduce 6 and 15. 3 goes into both of those. 3 goes into 6 2 times, and 3 goes into 15 5 times. So I end up with 2/5, right? Now, what is that as a decimal? Because notice my fractions don't have the same denominator. And when they don't have the same denominator, it's hard to compare them. So let's make them have the same denominator. Or let's not even make them have the same denominator. Let's convert them both to decimals, just like I did for the theoretical probability. So I'm going to put in my calculator 2 divided by 5, and I get 0.4. Okay, so now I'm comparing my two decimals. So I have 0.4 compared to 0.3 repeating. Which one is bigger? Well, this one right here is bigger. So I know that the experimental probability is higher than expected. And that's what I'm going to write where it says compare. So higher than expected. So what I know is that when we did choose the numbers between 1 and 3 30 times, we chose 2 12 times, and that was more times than I would have expected it to be chosen based on the theoretical probability. Okay, let's move on to number 2. The spinner below is spun 60 times. The results are shown in the table below. Okay, so A, find and compare the theoretical probability and experimental probability of spinning an A. Okay, so first thing I need to know is how many sections are on this spinner. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 sections on the spinner. That means that there are 12 total outcomes. Okay, and we want to know the theoretical probability of spinning an A. So how many favorable outcomes are there for spinning an A? Well, when I look here, I've got 1, 2, 3 A's. So we've got 3 favorable outcomes over 12 total outcomes. So 3 over 12. That reduces. 3 goes into both of these numbers. 3 divided by 3 is 1, and 12 divided by 3 is 4. So I get 1/4. Well, when I put in my calculator 1 divided by 4 to make this a decimal, I get 0.25. And remember, I'm just changing it to a decimal so it's easier to compare because my fractions might not have the same denominator. Okay, so now let's talk about the experimental probability of choosing an A. So we know that the spinner is spun 60 times, and the results are shown in the table. So A, it landed on A 18 times. So 18 is the number of favorable outcomes. That's my numerator. And remember, the spinner was spun 60 times. So that's my denominator. Now 18 divided by 60, I know I can reduce that. So I know that 3 goes into both of these numbers. 18 divided by 3 is 6, and 60 divided by 3 is 20. I see I've got 2 even numbers, so I know that 2 goes into both of these. So 6 divided by 2 is 3, and 20 divided by 2 is 10. I can't reduce that any further, so that is my probability. And notice our fractions have different denominators. So I'm going to make them both decimals. So 3 divided by 10, when I put that into my calculator, I get 0.3. Okay? So now I'm comparing my 2 decimals, 0.3 and 0.25. Which one's bigger? Well, this one here is bigger. So I know that the experimental probability is higher than expected. So where it says compare, that's what we're going to write. Higher than expected. Because remember, the theoretical is what we expected to happen, and the experimental is what actually did happen. So the experimental probability is higher than expected. Okay, part B, find and compare the theoretical probability and experimental probability of not spinning an A. Okay, well, like we said, for theoretical, what should happen? There are 12 sections, so I know that 12 is my denominator. And the sections that are not an A, well, if there's 3 A's, that means that there are 9 sections that are not A's. And I can just verify that by counting. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, I was right. So 9 out of 12. Well, does that reduce? I know that 3 goes into both of those numbers, so 9 divided by 3 is 3, and 12 divided by 3 is 4. So I get 3/4. And 3 divided by 4, when I put that into my calculator, I get 0.75. Okay, so now let's talk about the experimental probability. So we know that A was selected 18 times out of 60. So how many times were B and C selected? Well, if I add these two together, 20 plus 22 is going to be 42. So 42 is the number of favorable outcomes, and I divide that by the total number of outcomes, 60. The spinner was spun 60 times. Well, does this reduce? I know that 2 goes into both of these numbers. 2 goes into 42 21 times, and 2 goes into 60 30 times. Well, these numbers are both divisible by 3. 21 divided by 3 is 7, and 30 divided by 3 is 10. I can't reduce that any further, so that is my probability, my experimental probability. But what is that as a decimal? Well, 7 divided by 10 is going to be 0.7. Okay, so now I'm going to compare my 2 decimals. So we have 0.7 and 0.75. Now keep in mind, this is really 0.70. So I'm comparing kind of the 100th spot because the 10th spot is the same. Well, 5 is bigger than a 0 right here. So that means that this time the theoretical probability is higher than the experimental probability, right? So what would we write when we compare? Well, we would say that the experimental probability is lower than expected. Okay, let's move on to number 3. A member of a soccer team is chosen at random 40 times. Results are shown in the table below. So A, find and compare the theoretical probability and experimental probability of Reese being chosen. So we see Reese in our table right here, right? Now, how many people are on this team? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 total outcomes. That's going to be my denominator. And how many of them are Reese? Well, when I just read through the names, I only see 1 Reese right here, so 1 favorable outcome. So 1 divided by 10, when I put that into my calculator, I get 0.1. Okay, so now that's what should happen. Let's talk about what actually happens, okay? So I know that we chose a team member 40 times. So 40 is going to be my denominator. Okay. And then how many times was Reese chosen? Well, it says right there 2 times. So 2 favorable outcomes out of 40. Does that reduce? Those are both even numbers. 2 goes into both. So 2 divided by 2 is 1, and 40 divided by 2 is 20. Well, 1 divided by 20, when I put that into my calculator, I get 0.05. Okay, so that is my experimental probability, and this right here is my theoretical probability. So we have different denominators, so let's compare our decimals. So I have 0.1, that's like 0.10, and this right here is 0.05. Which one's bigger? This one here is bigger. So what could we say about the experimental probability? Well, it is lower than this one, so it is lower than expected. That means we would have expected Reese's name to be chosen more than just 2 times. Okay, now let's look at B. Find and compare the theoretical probability and experimental probability of a boy being chosen. And just to make it easy, I highlighted the boy names and the girl names. So the boy names are in blue. So I see 1, 2, 3, 4, 5, 6. 6 boy names. And remember, there were 10 people on this team. So there are 6 favorable outcomes out of 10 total outcomes. We can reduce that. 2 goes into both of those. So 6 divided by 2 is 3, and 10 divided by 2 is 5. So 3/5. Now, what is that as a decimal? Well, 3 divided by 5 is going to be 0.6. Okay, now let's figure out our experimental probability. So I have to add up all of these numbers for the boys. So 4 plus 6 plus 5. When I add those up, I get 15. And now I've got 3 plus 5 plus 2. Well, 3 plus 5 is 8 plus 2 is 10. So boy names were chosen 15 plus 10, 25 times. So 25 times, 25 favorable outcomes out of 40 total outcomes. Well, does that reduce? I know 5 goes into both of those numbers. 25 divided by 5 is 5, and 40 divided by 5 is 8. So I get 5/8, right? Well, what is that as a decimal? 5 divided by 8 is 0.625. Okay, so now I've got my theoretical and my experimental probability. So we're comparing our decimals because our denominators are different. So 0.625 and 0.6. Remember that 0.60. So I've got to compare my hundredth spot. So I'm comparing a 0 to a 2. Which one's bigger? Well, this 2. So we could say that the experimental probability is higher than expected. That means that boy names were chosen more than we expected them to be chosen. Okay, let's move on to page 14. So a card from the following set is chosen at random 120 times. Results are shown in the table below. First of all, how many cards are there? When I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 cards. That means that there are going to be 15 total outcomes. So when I do my theoretical probability, my denominator should be 15. Okay? So theoretically, if a card is chosen 200 times, how many times would you expect to pick a card without stripes? Okay, so cards without stripes. Well, that first one has stripes. Here's one without stripes. That's a solid. 3, 4, 5, 6, 7, 8, 9, 10. So the only ones I didn't highlight around are the ones with stripes. So we have 10 cards without stripes. That means we have 10 favorable outcomes out of 15 total outcomes, right? Now, I could reduce this, but it's not necessary because we want to know that if a card was chosen 200 times, theoretically, how many would we expect to be without stripes? So I'm going to multiply this fraction by 200. So in my calculator, I'm going to type 10 divided by 15 times 200. And I'm going to see what I get. So So 10 divided by 15 times 200. And I get 133.3 repeating. Now, I can't pick a card like a partial time, so I need to round. So we're going to say about with the squiggly equal sign. And because I've got a 3 right here, I'm going to round down. So I'm going to say about 133 times. And that right there is my answer. Okay, now based on the experiment, if a card is chosen 200 times, how many times would you expect to pick a card without stripes? Okay, so when I look at my table, stripes was selected 42 times, right? So how many times did we pick? 120 times, right? So I'm going to say 120 minus 42. And 120 minus 42 is 78. So a card without stripes was selected 78 times. Hold on, I'm going to close the door because I can hear people coming. So give me 1 second. Okay, so we know that a card without stripes was chosen 78 times. So 78 is going to be my numerator. That's the number of favorable outcomes. And my denominator is 120 because it tells me right here 120 times. So 78 over 120. Now it's still, if a card was chosen 200 times, I could reduce this, but it's not necessary. I'm just going to multiply times 200. Okay? So in my calculator, what I'm going to type is 78 divided by 120 times 200. And I'm going to see what I get. So 78 divided by 120 times 200. And I get 130. I get an even number, 130. So that's my answer, 130 times. Will you close that door for me? Okay. Let's move on to number 5. A marble is picked from the jar 60 times. Results are shown in the table below. Okay, well, I need to know how many marbles are here. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Did I miss any? Yep, 32. So 32 marbles. Can y'all please keep that door closed? So there are 32 total marbles, okay? So that's going to be my number of total outcomes. It's going to be my denominator in my theoretical probability, okay? So I'm going to have something out of 32. Now, theoretically, if a marble is chosen 150 times, how many times would you expect a gray marble? Well, how many here are gray? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 marbles are gray. So 14 is my number of favorable outcomes. So 14 over 32. Now it's not necessary to reduce that because we're trying to predict if we choose 150 times, how many times would we get a gray marble? So I'm just going to multiply this fraction times 150. So what I'm going to type into my calculator is 14 divided by 32 times 150. And I'm going to see what I get. So 14 divided by 32 times 150. When I put that into my calculator, I get 65.625. Okay, what we know is we can't pick a marble 0.625 times. So we're going to have to round. And because that's a 6, I'm actually going to round up. So I'm going to say about 66 times. Okay, now we want to know based on the experiment. If a marble is chosen 150 times, how many times would we expect a gray marble to be chosen? Well, right here, we see that gray was chosen 28 times. So 28 is my numerator, and my denominator is going to be how many times marbles were picked. It says 60 times. So we have 28 over 60. But if we choose 150 times, so we're now going to multiply that times 150. and we're going to see what we get. So in my calculator, what I'm going to type is 28 divided by 60 times 150. So 28 divided by 60 times 150. And I get an even number. I get 70. So 70 times. Okay, let's move on to the last one, number 6. A piece of fruit was selected. Can someone please close that door? A piece of fruit was selected from a basket 40 times. The results are shown in the table below. Okay, theoretically, if a piece of fruit is chosen 300 times, how many times would you expect to pick an apple or a banana? Well, how many total fruits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 total fruits. So that means there are 20 total outcomes. So for my theoretical probability, 20 is my denominator. Now, how many of them are an apple or a banana? So there's 1, 2, 3, 4, 5, 6, 7. So 7 apples or bananas, right? So 7 is the number of favorable outcomes. That is my numerator. But we want to know if fruit is chosen 300 times, how many would be an apple or banana? So I'm going to take that fraction and multiply it times 300. So in my calculator, I'm going to type 7 divided by 20 times 300. And let's see what we get. 7 divided by 20 times 300 is equal to 105. So equals 105 times. So that's my answer. That's what we would expect. Now let's look at the experiment. Based on the experiment, if a piece of fruit is chosen 300 times, how many times would you expect an apple or a banana? Okay, so we're looking at our table here. We know that fruit was chosen 40 times, so all of these numbers here add up to 40, right? So my denominator is 40. Well, what is the number of favorable outcomes? Well, when we look in our table, apples were chosen 8 times and bananas were chosen 4 times. 8 plus 4 is 12. So that's my number of favorable outcomes. 12 divided by 40 is my probability. I don't need to reduce that. I can just go ahead and multiply by 300 because we're choosing 300 times. So in my calculator, what I'm going to type is 12 divided by 40 times 300. So 12 divided by 40 times 300. And I get 90. So 90 times is what we would expect based on the experiment. That is the end of this video. Y'all have a good day.